Hello, I will introduce our CVPR paper called CiaoSR, Continuous Implicit Attention in Attention Network for Arbitrary-Scale Image Super Resolution. Most existing arbitrary-scale SR methods use a local ensemble, and the ensemble weights are equivalent to the bilinear interpolation. It means it has no learnable parameters and ignores the similarity of the visual features. And it also has the limited receptive view and cannot ensemble non-local features in the large view. Different from classical image super resolution method, they consider the image as discrete data and super resolution for different scale as independent tasks. It means they need to train the multiple models for these scales. For this work, we propose a new implicit model to generate continuous scale image by one single model. This is an architecture of our CiaoSR. The architecture mainly contains the backbone, continuous implicit attention in attention network, and embedded scale-aware attention network. In this figure, given an LR image, the model first extracts the latent code using the backbone. The continuous implicit attention in attention network learns the local ensemble weight and integrates the local and non-local features extracted by the scale-aware attention network. Given pairs of the coordinates and the latent codes, we first calculate the similarity of the queried feature and the key features in the local region. Here, the queried features are the nearest feature from the query point, and the key features is related to the concatenation of the latent code, coordinate distance, and the scale information. Then we use the source function to have the ensemble weights. Last, we use the weights to fuse the various features. And the various features we consider local and non-local feature. Different from the standard self-attention, we model the coordinate in our attention. To use the non-local information, we embed a scale-aware non-local attention module. First, we obtain the query and value features from the latent code, and downsample the latent code to the scale as the key features. Then we calculate the pixel-wise similarity between the query located at ij and the key on other coordinates. Last, we use the source for the similarity matrix to aggregate the features in an image. For the arbitrary scale SR task, all models are trained on the IV2K dataset, and we test on standard benchmark datasets. We use RDN and swing IR as the backbones by removing the R sampling module. This will mainly consider the previous state-of-the-art arbitrary-scale SR method. This table shows the quantitative comparison with the state-of-the-art method for in-scale and out-of-scale SR on benchmark datasets. In-scale means the discrete scale are included in the training, and out-of-scale means the model do not see the scale before. It helps to evaluate the generalization performance of the models. For the same backbone, our model has the highest PSNR, and across the different backbones I marked in the table, we can see that the worst backbone RDN with our implicit model can outperform the better backbone swing RR with the pixel 4. In this figure, we provide visual comparison with other arbitrary scale SR methods. Our generated SR image has sharper texture than other methods. For example, our model can restore the texture of the building and tennis racket, although the texture in the LR image are degraded. Other methods can only restore part of the texture, probably due to the limitations of the local ensemble and insufficient features. For the ablation study, the first table shows the importance of the attention in attention network and the scale-aware non-local attention module. The second table evaluates the effectiveness of the single scale, multiple discrete scales, and continuous scales. Training the backbone with our implicit model with single scale has an improvement over the original assembly module. And training with multiple discrete scale has a better performance than single scale because the module can use the correlation information of different scales. Our model has the further improvement when training on the continuous scale. To compare the effect of the synthesis steps for the large scale image, we can generate an image by 3 steps or 2 steps. One step has a better performance because the area can accumulate around the multiple steps. For the efficiency of the model, our model has a higher performance gain, although it has much more inference time because it searches the non-local features in an image. This paper proposes a new architecture and has the best performance and good generalization ability on both in-scale and out-scale distribution. And our model can be used behind any SR backbone to boost the performance. Thanks for your attention.